Yeah, good morning guys. So please type in the chat box, am I audible? Is the audio and video clear? Just a second. Yeah, fine. So I think the audio and video is fine, right? So in today's lecture, we'll try to look at some introduction to compressible flows, but again, we'll try to look in detail of boundary layers, dimensional analysis, and also a bit of some basic turbulence. Okay, Vivek, I hope I'm clear, right? Yeah, good morning all of you. Welcome back to this session. So in this lecture, we'll majorly focus on boundary layers. Then we'll see the importance of dimensional analysis. This is a very important chapter actually in real physics point of view, and also turbulence we'll see, and all along we'll also try to solve certain numericals. Okay, now let us see. In the last lecture we have talked about plane Poiseuille flow. We have talked about plane Poiseuille flow and also Hagen-Poiseuille flow. Hagen-Poiseuille flow. Okay, now we have seen certain important understandings here. This is basically flow through a pipe. Flow through a pipe, and also here in case of plane Poiseuille, this is basically flow between two fixed plates. Flow between two fixed plates actually. Okay, so this is flow between two fixed plates. In case of this flow through a pipe, we have seen certain important things like what is the velocity profile and all, correct? So we have seen the velocity profile. Normally if you take a pipe, for example, in a pipe, if you have a pipeline like this, then with respect to radius, and this is the z coordinate, so we have Vz is equal to r square by 4 mu, so capital R square by 4 mu times minus dp by dz into 1 minus small r square by capital R square. So we have seen what is the velocity variation, shear stress variation. Good morning Anjit. So what is the shear stress variation, what is different, how we can calculate discharge. So we have seen certain things actually in this case. Okay, now in today's lecture, and we have solved certain problem as well in the last. In today's lecture we will majorly talk about boundary layers. Okay, how many of you, first of all, before starting the session, I want to ask you, how many of you are not comfortable with boundary layers, or how many of you don't feel like when you try to solve boundary layers, watching you to boost confidence. Okay, thank you. But tell me first of all, how many of you are not familiar or not very comfortable with boundary layers? Normally कॉलेज में पढ़ाया था लेकिन उतना ठीक नहीं है, किसी को लगता है ऐसा? Fine. Anyway, we will try to start this boundary layers. I'll try to spend certain enough 1.5 hour time dedicatedly on this boundary layers, and we will try to understand what is displacement thickness, momentum thickness, kinetic energy thickness, what are different fundamentals of boundary layers. Okay, now first of all, let us see. To see boundary layers, we have to understand what are external flows. External flows. Okay, so let us suppose if you have some body in the flow field. For example, let us say there is some solid like a sphere or a cylinder, for example, and let us say some fluid is coming, approaching this at a velocity u infinity. Then clearly this fluid will actually surpass, this means basically this fluid will flow over this solid, right? No, only half knowledge. Okay, sir, it's okay, fine. See here, so this is some sort of solid. Then what happens here, this fluid when it approaches here, clearly it takes a diversion like this, correct? So it's really important for us to understand what is the effect of this fluid in this regions where the fluid is actually getting diverted, and also the flow over this solid. Like for example, if you take an aeroplane, okay, aeroplane actually fly in air, and clearly whenever aeroplane flies in air, aeroplanes are the objects which fly within that Earth's atmosphere. So clearly fluid air is there at any point, and atmospheric air will actually flow over the aeroplane, because of which we can actually fly the planes. Okay, you cannot fly an aeroplane, means using the concepts of aeroplane, you cannot fly any object in the outer space. Okay, rockets and all, there's some sort of different physics that happen, but in atmosphere, whatever the objects that fly within the atmosphere, then clearly you need to study the effect of this external forces. Now in this discussion, since to analyze this, what we do is we take two components, like you can see at any point we'll take two coordinates. This is x and the normal to this is y. X is called streamline coordinate, and y is called cross streamline coordinate. Okay, so y is called cross streamline coordinate. At any point, if you take a tangent to this, the tangent will come like this, and this angle between them will be 90 degrees. Okay, so this x, like for example, if you call this x dash, which is the tangent direction, so at any point in the flow, this x dash and y remain perpendicular, but their orientation can keep on changing. Did you understand my point? Like at any point in the flow, if you start analyzing this fluid, then definitely what happens, this x dash tangent direction changes, and corresponding to the tangent, this y also changes. So the orientation of x dash and y change, but they remain perpendicular at all instants. Okay, matlab these two are always perpendicular. Clear? So like this, we set up a typical coordinate system to understand how things happen in this case. Is this clear to all of you? Okay, now let us see some small example of a flat plate which you could understand in a bit easier sense. Flat plate. Using flat plate, I want you to understand some things. See, let's suppose there is a flat plate here. For example, there's a flat plate like this, and some fluid is approaching this at a free stream velocity. Normally you call this free stream velocity, u infinity. Okay, so this is called free stream velocity. Now guys, these things what I'm going to tell you are really important, so please try to understand. We will see mathematically how things can occur, but first of all, let's try to understand the physics. If this fluid is traveling, if this plate is not here, the fluid might have traveled at same u infinity velocity, but the presence of this plate is like acting like a brake, mechanical brake to the motion of this fluid, correct? Now tell me one thing, whenever the fluid particles, let us suppose if you take this particular layer of fluid, when this layer starts traveling like this, definitely by the time it comes here, this plate will actually, because of viscosity, this mechanical inertia of this fluid will come down, and means velocity will actually come down. So if you compare the velocities here at location A and at location B, can anyone tell me out of these 2 points, at which point the fluid velocity is high? Point A or point B? So please tell me, when this plate acts as a mechanical brake to this fluid, when the fluid layers pass over this particular plate, then if you compare velocities at these 2 points, point A and point B, at which location velocity is high actually? Point A, correct? It's simple, right? Because if you have a vehicle, for example, if you apply brake, then definitely as the vehicle progresses, velocity comes down. Okay, simple logic. A and B. Also, I want you to ask one more thing. If you take a different layer of fluid, for example, which is very close to this plate. For example, if you take very close to this plate, then if you take these 2 points A and C, then out of these 2 points A and C, which point has higher velocity? Can anyone tell me which point has higher velocity? Again, it's point A, correct? Again, the point A has higher velocity, because compared to the second layer, which I have marked in yellow, like for example, if I call this first layer and second layer, compared to first layer, second layer will experience a slight less impact of the plate, because this layer 2, even though it's not in direct contact with the plate, but still layer 2 somehow knows that there is a plate here. Why? Because every fluid has something called viscosity, and this property is actually the messenger, or this property is actually the thing which actually tells this layer the impact of this plate, correct? Because the layer which is in direct contact with the plate will stay stationary. So this stationary layer, because of this viscosity, will try to pull the above layer slightly back. Okay, and this process will keep on happening, and clearly velocity at A is greater than velocity at B. Also, velocity at A is greater than velocity at C. Which means one thing you can understand, as you go in the y direction, like for example, if I set up the same coordinate system here, okay, so if this is x and if this is y, then clearly you can understand in the direction of x there is velocity gradient, in the direction of y also there is some velocity gradient. Yes or no? So dou u by dou y exists, dou u by dou x also exists actually. Now in actual practice, in many cases we see okay, we'll talk about it later. So first of all, this A, B velocities at these 3 points A, B, C are connected in this way. Now try to understand one thing. flow cannot occur across streamlines, correct? So flow can't occur across streamlines. Okay, so like for example, if you have a two streamlines like this, let us suppose if this is psi is equal to constant 1 and psi is equal to constant 2, then clearly whatever is the fluid flow happening at this section, same should be the fluid flow happening at this section, because meanwhile no flow can actually cut the streamline, correct? Now if that's the case, try to understand one thing. The layer of the fluid which is in contact with the plate is like this. Okay, let me take a new page so that you can understand. There is a plate like this, okay, and the flow actually happens in this direction effectively at u infinity. So if you take the streamline of that layer which is actually in contact with the plate, this is like this. Now this is one more layer of fluid, but you know, as the flow happens in this direction, velocity decreases. So definitely the streamlines has to diverge like this as they move in the x direction. Understood? So you can understand if this is actually your x direction and this is y direction. Now clearly the flow between these two streamlines, let us suppose if this is psi is equal to c1 and this is psi is equal to c2, then between these two streamlines, if flow is actually fixed, okay, it won't diverge this much. Actually it's a slight diversion. You can see generally it happens something like you know, very loosely I have drawn this diagram. So you can see there is slightly divergence of this streamline. The reason for this is between these 2 points, or between these 2 layers, whatever is the discharge here, same should be the discharge here, but clearly compared to the velocity of the flow at these points, velocity of the flow at these points is less. So since discharge is equal to area into velocity, as you progress along x direction, this velocity will decrease. I mean, if you write u, x component of velocity for example, effectively if you write u, this u decreases, but this has to remain same. So definitely area of the flow should actually increase. That's why in the direction of the flow, definitely whenever there is an obstacle, the streamlines will actually diverge in this flow direction. Is this concept clear to all of you? Streamlines will actually diverge, means they will actually get displaced in the y direction. Sorry, on y it's increasing. So why that the line is not diverging downwards? Because downwards there is a solid boundary, okay, you cannot penetrate inside. Got it? This is actually a solid. This is solid, right? This is solid. So clearly no penetration. No penetration condition. Understood? So streamlines will actually diverge in the flow direction. Is this points clear to everyone? Okay. Now let's see. So similarly, if you take any streamline, they'll also diverge like this. Okay. So streamlines actually diverge in the downstream direction. Streamlines of the flow diverge along flow direction, along downstream. Okay, so they keep diverging like this. Now once you understand this much, practically it's an internal flow or external flow. The flow physics or the mechanics of the flow, or basically the momentum equations, they remain same. Continuity equation should be satisfied, whether it's an internal flow or external flow doesn't matter. It's a fluid flow at the end. So continuity equation and also momentum equation has to be satisfied. Okay. Now we have identified solving this momentum equation. Like for example, for any flow, continuity tells you, of course, incompressible. Okay, for any incompressible flow, we are not taking compressible effects right now, so only incompressible. Then you have divergence of velocity in 3D. Like for, okay, let us suppose if you are writing in 2D, in z direction you are not changing anything. Z is very large, so that any disturbance gets nullified. Okay, so is there any pressure gradient also? Will come there. Okay, just give me some time. Sorry, I couldn't read your name, Wazim, but yeah. So just give me some time. I'll in next 5 to 10 minutes you will get clarity what's happening to pressure. Okay. Now see here, this is momentum equation. That's why I'm writing momentum equation. Momentum equation. Normally I write mom generally momentum equation. So if you see, this momentum equation is like rho x bar body force minus pressure gradient plus mu into del square v is equal to rho times dv by dt actually here. Now this is the equation. So practically we know that solving this equation is not, even till today it was not solved actually, but we have solved this equation only for very simple cases. We have seen in case of 𝐂𝐻 flow or plane Poiseuille or even in Huygens-Poiseuille, we make majority of the terms in this equation 0 and try to convert this to ordinary differential equation, and then we will go for the solution. Okay, but without actually solving this equation, you can try to understand few things actually. Okay, so what are the few things that you can understand? Let me tell you. When you have this plate like this, definitely one point that you can understand is, if this stream is coming at u infinity, then this fluid layers will actually slow down, correct? So you can see this fluid layers will actually slow down. They're not exactly straight lines, but you know, you can just, then you know one thing, at this section and also at this section, if you analyze particles velocities, for example, clearly at these 2 points velocity is 0 because of no slip. If you fix this plate, for example, okay, so if you fix this plate, because of no slip they are 0. Then comparatively at this point and this point, if you consider the flow velocity, definitely if this is 1 and this is 2, v1 is greater than v2. Okay, if you keep on going, velocity keeps on increasing from 0 and it slowly increases because the distance from the plate is increasing, so the effect of the plate keeps decreasing. At one particular point you reach a velocity which is very close to u infinity. I'm not writing equality sign, it is very close to u infinity. Sometimes you actually define it as velocity is equal to, at that point, 0.99 times u infinity, which is 99%, or 0.999 u infinity. It depends on your research accuracy, like whether you want to go to 99% or 99.9% or 99.99%, it depends. Okay, so I'm not writing equality sign, but it's very much close to u infinity. Normally in, at your level we can see, or at our level we can see, it's like 99% of the free stream velocity, but in general it can go to any constant. Okay, the main intention is we'll try to touch this u infinity asymptotically. Asymptotic is, you know it, what is asymptotic? Let us suppose if this is u infinity, we will try to reach this velocity like this. Okay, we cannot exactly say it's equal, but it's approximated. Okay, now if this is u infinity, then this thickness or these layers of the fluid are very much close to this solid boundary, and this layer of the fluid is called boundary layer, and this is the layer of the fluid in which the effects of the boundary are felt very strong. Understood? Clear? So this is the layer of the fluid in which the effects of the boundary are very much high, because the boundary is pretty much close to these layers and the boundary can transfer its effect very effectively within this region. Okay, and that's called boundary layer, and the thickness of this layer is called boundary layer thickness. That's it, it's delta. Okay, so normally it is denoted by delta. Boundary layer thickness, boundary, yeah, correct, boundary layer thickness, which is actually delta. Now let us suppose this is x coordinate and y coordinate. Again we want to analyze certain things, because somebody has asked me what happens to pressure. Okay, we'll see what happens to pressure. Now in this case, this is delta, is called boundary layer thickness. Tell me one thing, at all these corresponding points, if you see, like for example, if you take this layer, compared to this velocity will be less, correct? So if you want to touch u infinity at this location, tell me this thickness should be more or less here in this case. Let us suppose if you call this section 1 and section 2, here after traveling a distance of delta you have reached approximately u infinity. Now at this section, when you know the particles are getting slowed down, then if you want to reach u infinity, the distance you have to travel will be more than this delta or less than this delta? My question is, if you want to touch a layer of u infinity at section 2, you have to travel a distance which is more than this delta or less than this delta? More than this delta or less than this delta? It should be more, correct? It should be more than this delta, right? Because here, since these particle velocities are high, you can touch delta within a less distance, but here by the time you reach section 2, the fluid particles are getting slowed down. So to reach this u infinity, you have to travel a distance which is higher than this particular delta. So let us say this is delta at this location. Okay, so delta increases. So boundary layer thickness is distance between u0, yes, u0 and 0.99 or 0.999 times u infinity. Okay, in the transverse direction, not in the flow direction. Clear? Now, if this is delta, one thing you can understand physically, till now we haven't done anything, but one thing you can understand physically is, if this is x, you know, as x increases, delta also increases. This is what you understood. Correct? Yes or no? Type in the chat box. Is this point clear to all of you? We haven't done any maths right now. We are just trying to explain the things using physics. That's happening here. Okay. Now, let's see if this delta also increases. I want to ask you one more thing. For example, if you take velocity gradients, u by y or dou u by dou y, for example. Okay. If you take the, because right now we cannot say that u is not function of x, u is not function of y and all, because u is also function of x. Clearly you can see as x increases, u will actually decrease. Okay. So therefore you can write only partial derivatives, not exact derivatives. Now, if you talk dou u by dou y, in this point, guys, little bit of simple mathematical calculus, very small. See here, if you see this section, section 1, to go from 0 velocity to u infinity, approximately u infinity, you need this much distance. But here, if you see, to go from the same 0 velocity to same u infinity, you have to travel a distance which is larger than this. Which means, out of these two locations, can you tell me at which section this is high? The gradient. This is nothing but the rate of change of velocity, correct? So, rate of change of velocity is fast in which of these two sections? 1 or 2? You want to understand these things. Come on. Tell me. Here, to go from 0 velocity to u infinity, a distance of delta is needed. And here, in this case, to go from same 0 to u infinity, you need a larger distance. Then can you tell me in which case the velocity gradient is fast, or basically velocity gradient value is high? Clearly at section 1, correct? At this section 1, with increase in y, u is changing or u is increasing fast, correct? So at section 1, which means clearly this value at section 1 is greater than this value at section 2. And later when you do bit of mathematics, you will also understand that dou u by dou y at y is equal to 0 at section 1, or this value decreases as x increases. As x increases. Now, if you take this fluid to be Newtonian, all these things, wall shear stress means the shear stress at the plate, wall shear stress, which is nothing but tau w, which is mu into dou u by dou y at y is equal to 0. So, if you see, if this quantity is decreasing as x increases, then definitely this decreases as x increases. Correct? So if you take 2 points, like for example point 1 and point 2, definitely the wall shear stress acting at this point is high as compared to wall shear stress acting at this point. Okay, so tau w1, for example, if you call this points 1 and 2, so tau w at x1 is actually greater than tau w at x2. Clear? Yes or no? This might be slightly not intuitive, because a general expectation will be if the shear stress is high here, why the fluid is reaching u infinity very low? Okay, that we have to do certain mathematics to understand. But right now, physically, can you understand using this help of velocity gradients mathematically that this quantity shear stress at as you go in the x direction, the wall shear stress will actually come down. Okay, mathematically we'll see what happens later after we do the von-Karman's momentum integral, which I'll show you now. Clear? So does the boundary layer thickness highly sensible to flow type, like it's rotational? Definitely. During turbulence and all, it increases. We'll see different cases. We'll see first the assumption that delta is actually very small, which is generally the case in many of the laminar flows. Okay, laminar boundary layers in general. Okay, is this clear to all of you? These 2 points, are they clear? As x increases, this delta also increases. As x increases, this wall shear stress decreases. Is these 2 points clear? It do depends on rotational or irrotational, we'll see. Okay. So is this clear to all of you till this points? please respond, because boundary layer is that particular topic where it should be like a mutual talk. If I keep on talking, you may not understand certain things. Okay, now, oh sorry, yeah, now let us try to see which terms are important and which terms are not very much predominant in this boundary layer equation. Okay, so let us try to derive boundary layer equations to understand some physics. Boundary layer equations. So what are the equations you have to solve in order to talk something about boundary layers? And these are simplified forms of Navier-Stokes equation. Navier-Stokes equations. Okay, so let me take some example of a flat plate which you can generally understand. Now here you have u infinity, you have the x coordinate, and also you have the y coordinate. Okay, so you also have the y coordinate like this. Then one thing that you observed, as x increases, delta increases. So let us suppose right now I am drawing a graph to convey that as x increases, delta increases. So this is delta versus x. You can understand, as x increasing, this delta is also increasing. Okay, so this is what we have. Please summarize once. Yes, so we are summarizing. Actually, in this case, first of all, streamlines will diverge because of the velocities getting decreased as the flow happens. Then secondly, you can understand at these 2 points, since here the velocities are decreasing, then clearly as you travel, the distance required to reach u infinity increases. So that indirectly means as x increases, boundary layer thickness will increase. And also, as per this velocity gradient discussion, you can understand this tau w at x1 is actually greater than tau w at x2, means the wall shear stress will decrease along the x direction. Okay, now coming to this, so that's delta versus x. Right now we don't know what is the equation for this delta versus x, but what you can say is that this delta will actually increase as x increases. Okay, so this is the boundary layer thickness variation with respect to x. It's not the fluid particle. Understand, many of you might have a wrong intuition that the fluid comes like this, hit the plate and it moves like this. Okay, no, that's not the case. Clear? Then let us see actual continuity, actual Navier-Stokes. If you write, continuity is same, dou u by dou x plus dou v by dou y is 0. Then you can understand in x direction, you can say dou u by dou t plus u into dou u by dou x plus v into dou u by dou y is equal to minus 1 by o. Of course, body forces we are neglecting, no body forces and all, plus kinematic viscosity times del square u actually. Okay, similarly in y direction, dou v by dou t plus u into dou v by dou x plus v into dou v by dou y is equal to minus 1 by o times dou p by dou y plus nu times of del square v actually. Okay, so this is what we have, and we are talking only in the 2 directions. In the z direction we are assuming nothing is changing. Okay, so del in Cartesian, let us take del square dou square by dou x square for dou square by dou y square. It's a 2D. Okay, so 2-dimensional Laplace we can take. Now before understanding out of this, you know, clearly one thing is known, these equations are not directly solvable, but in boundary layer equations we can make certain assumptions which makes us to solve these equations for some simple flows again. Okay, so if you try to understand, one assumption that I am making is here. Of course, you can have certain cases other than this assumption in very extreme cases, but right now in the general majority of the cases, this assumption what I am going to make will hold good. Okay, so if you take this length of the plate is L in general, and at any random location, for example if you take this as delta, then this delta is actually much smaller than this L. In practice also you might have seen, when you calculate boundary layer thickness values for some problems later, you will find out normally the plate length will be of 1 meter, 2 meter and all, but the boundary layer thickness will be only few mm, like 6 mm, 7 mm or 13 mm, 25 mm. This is the range generally that you will get the values. Okay, so one assumption that I am making here, this delta is very much less than L actually, and this will automatically imply the Reynolds number is very high. the Reynolds number is very high. Right now you can understand this physically, but mathematically how these two are equal, I'll show you a bit later. See here, when delta is very, very less, that means, try to understand, if this delta is small, what is the physical meaning of that? The fluid is trying to come, okay, the fluid tries to come into the plate, then there is viscous force and also there is inertia force for the fluid. If delta is very less, that means this plate is not able to show its effect up to larger distances. Means only this plate is capable of showing its effect only onto the fluid which is very near to this plate, correct? If delta is small, that means this plate cannot show its effect very strongly onto a very large distance, okay? It can show effectively onto a very small distance. That means even though the plate presence is there, the inertia of the fluid is so strong that it don't bother much about this plate, correct? Yes or no? Is this points clear? So please type in the chat box. Can you understand? If the inertia of the fluid is very high, that means even though there is a presence of plate here, the fluid doesn't care much and this effect of the plate will be very small. Means delta is actually very small in that point. Yes? Can I say this? Type in the chat box. All of you. Everyone should type. Are you all understanding the things? Yes? So, clear? Did you understand? If delta is less, that means the inertia of the fluid is actually large. Okay? So, you know clearly Reynolds is like inertia by viscous. So, if inertia forces are high, then definitely this Reynolds number will also be high. Okay? So, anyway, this is some physics understanding from this fluid flow, but mathematically also later we will see that how these two assumptions are actually same. Now, using this assumption, we do something called scaling analysis. Scaling analysis. So what is this scaling analysis? Okay. So scaling is basically that. Let us suppose if I have a value u, for example. Okay. Then we can talk about the order of magnitude of this. Magnitude. Like, for example, I can say roughly that this u, whatever you have inside, will be comparable to this u0. It may be half of this, 1/3 of this or something, but it's not like this is 1000 times of this. Understood? These two magnitudes are very, relatable is what I mean by telling order of magnitude. Understood? Like, you can see this u infinity and this u are closely connected to each other, but it's not like they are completely different. It's not like if u is 10, this is 1000, this is 100. It's not like that. Okay? Do we have any experimental techniques or empirical references of boundary layer calculation of bodies to set reference values? So many. Yes, even now in this course, in this class also we'll derive one. Okay? We'll see certain velocity profiles and we will derive actually. Okay, when you are analyzing boundary layers, the main important thing is to get the velocity profile. So once you get the velocity profile, we'll see certain techniques to calculate the velocity profiles. And once you get the velocity profiles, there is a well-defined mathematical calculations or even experimental techniques which can talk about the boundary layer thickness. Okay. Normally, how do you calculate the boundary layer thickness? We'll see experimentally how do you calculate, and also mathematically I'll show you. Okay. Now see here, this is the order of magnitude. Now one important thing I can tell is, we take something called scaling parameters. So see here, in this equation you have u, v, p and also v. Okay. First of all, one assumption, the assumption I'm making is steady flow. Okay. Things are steady, so no variation with respect to time. Of course, you can have unsteady terms also. Normally we'll see Stokes first, Stokes second problem. Right now we cannot see, but in this in the gate syllabus they are not there. But actually we can have certain unsteadiness, and you can see why this is actually called the momentum diffusivity. Okay, fine. Anyway, we'll see that later. But right now, scaling parameters. So u at any point can be scaled to u infinity. Correct? Because these two are of comparable order. Similarly, x coordinate at any location can be scaled to L. Okay, so x coordinate at any location can be scaled to L. When I'm writing scale, I'm not telling these two are equal. Okay, but the magnitudes of these two, maybe this x can be half of this or 1/10 of this, something like that, but it's not like these two are not at all comparable. Okay, they both can be compared in terms of magnitude scale. Then y. Now tell me one thing, this y, if you have here y in this direction, if you compare, because the main importance of these equations, whatever the things that we are going to do, we are going to do in this region, and we have already made one assumption, this delta is very much less than L. So actually comparing this y to this L is not much, is not of making more sense actually. Okay, if you see this y at this point may be very small, okay, because the boundary, I told you, length of the plate will be something like 2 meters or 3 meters in general, but the boundary layer thickness is only some few mm. So that's why this y, instead of scaling this to L, it doesn't make much sense. So what we do is we'll scale this y to delta at any point. So y can be scaled to delta. Did you understand this logics behind scaling these terms? This y I am not scaling with L, did you understand? Because in actual case, when delta is very much less than L, to do any analysis within the boundary layer, comparing this y with L is not of much sense actually. Clear? Because L is very large, but y is very, very small. It's like length is some 1000 to 2000 times of this y. Can't we make it 0? No, we cannot make it 0. If you make it 0, that's it. No need of doing boundary layers. Clear? So this is y delta. Now there are some other parameters. V can be scaled to u infinity delta by L. This is slightly non-intuitive, but I'll explain you physically what happens here. See, u infinity is very large compared to v, because in this layers the predominant velocity is in the x direction, so y components of velocities are very small. Now if y components of velocities are very small but u infinity is very large because that's the phase time velocity, then if you want to scale this v to this u infinity, you have to multiply a very, very small value which can make this product equal to v. Yes or no? Or in terms of magnitude, scaling to v. Clear? Understood? I'm telling this u infinity by itself is very large. So if you want to compare the orders of these two, if you want to make the orders of these two terms equal, you have to multiply this u infinity with a very, very small quantity. That small quantity what we are taking is actually delta by L. Clear? So physically you can use this term for the non-dimensionalization of this v. I'll also show you mathematically, because you can see when you have the continuity equation dou u by dou x plus dou v by dou y is equal to 0. You can see if you do the scaling analysis, this term will be of the scale u infinity by L, because change in u is like u infinity and change in x is like L, and this term is like scales to v by this y is scaled to delta. So if you see this, we'll see v is equal to minus u infinity delta by L from this. That means v and the magnitude of this both are comparable. Understood? So that's why I'm comparing this v with the u infinity delta by L. This is the physical reason why we are doing, and this is the mathematical from continuity equation why you can actually take this v scaling to u infinity delta by L. Is this clear to all of you? Okay? Is this term clear? Because every term you can understand easily, but this is the slightly non-intuitive term. That's why you cannot tell this directly, but with bit of logic you can understand that v can be scaled to this u infinity delta by L. Correct? Okay, is this clear to all of you? Now there is also one term which you can scale, which is pressure actually. So pressure can be scaled to rho u infinity square, because you can see lot of experiments tell this, and also normally from your Bernoulli's equation, if you neglect the potential effects, you can see order of pressure is like order of rho v square by 2 actually. Okay, this half we are neglecting because anyhow we are doing only scaling, not writing the exact equations. So this p will be in the range of this rho u infinity square. This is the scaling of pressure, this is the scaling of velocity, and this is scaling of y, x, and also u. So you have u, v, x, y, and pressure. You covered all the quantities. Okay, so these are the quantities which I'm going to use for the understanding of these two equations, and to see which terms out of all these terms, which terms are having high weightage and which terms are having low weightage, or which terms has high magnitude and which terms has low magnitude in general. Clear? Look, I'm repeating this from continuity equation. This change in velocity will be in the range of this u infinity. Change in x can be compared to this L. Similarly v, we don't know, we want to get, so scaling of v, and this change in y can be scaled to delta. So from this equation v can be written in the orders of u infinity delta by L. That's what I have written here, and this is normally from Bernoulli's equation and also from many experimentations. You can see easily pressure can be easily scaled to rho u infinity square. Okay, now let us see. Now if you see these equations, first of all let us write with y equation, y momentum equation. You can understand something. Y momentum equation, u into dou v by dou x plus v into dou v by dou y is equal to minus 1 by rho times dou p by dou y plus nu times of dou square v by dou x square plus dou square v by dou y square is what we have here. Now, in this equation, let us try to see the magnitude of each term. Okay, I'm not talking about the exact values. Let us try to see the orders of magnitudes of each and every term. Like for example, let us suppose the magnitude of this is in the thousands and the magnitude of 10,000s, and let us suppose if you see the magnitude of this is only 10, then definitely you can neglect this term in this equation, correct? So that's how. Let us see certain things. Using this assumptions what we have made, let us try to see because it's really difficult to solve all these terms once, if all these terms are present in this equation, we cannot solve this equation, okay? So let us see whether we can delete some terms which could make some importance. Now, if you see this magnitude will be u will be of order u infinity, v will be of order u infinity delta by L, x will be of order L actually, correct? This term, if you scale, v will be of order u infinity delta by L. This change in velocity will be again of the order u infinity into delta by L by y. So y you can scale to delta. This term 1 by rho into pressure you can scale to rho u infinity square, y you can scale to delta. First term can be scaled to nu, v can be scaled to u infinity delta by L. This x square can be written as L square actually. This term can be scaled to v again, nu again. So v is u infinity delta by L by y square. So y square is actually delta square. So this is what we have here. So try to understand, is this equations understandable? Did you all understand how I have written this? Because wherever there is u, we have scaled to u infinity, wherever there is v, we have scaled to u infinity delta by L, and wherever there is x, we have scaled to delta, wherever there is y, we have scaled to delta actually here, okay? And here you can see this dou square v by dou x square gives only the change in one velocity divided by this 2x square, because this v is actually single here and square is on the top of x square. Understood? Is this clear to all of you? Did you all understand? I am telling the magnitude of this term will be within this range, the magnitude of this term will be in this range, the magnitude of this term will be in this range, and like that similarly for all the terms. Clear? Is this clear to all of you? Yes? Now let's try to understand. If you compare the magnitudes of different terms, you can understand one thing. If you compare these two terms, for example, okay, so if you compare these two terms, then clearly you can understand one thing. This term is of magnitude mu u infinity delta by L cube. This term will be of order nu u infinity delta by L into delta square. So if you take this delta by L, here also let us write delta by L by L square. This is delta by L by delta square, okay? So this is like delta by L by delta square, okay? Now tell me one thing, delta is much less than L. That means out of these two terms, like very much small, delta is very much small than L. Then out of these two terms, if you call this first term and second term, out of these two terms, which term is highly powerful? Or if you compare the magnitudes of these two, we can neglect one term. Can you tell me which term we can neglect? Out of these two terms, because it's a summation, okay, it's a summation of these two terms. So out of these two terms, we can actually neglect one term. Can you tell me which term we can neglect? Which term we can neglect actually in this case? Come on, think. This will be of magnitude this quantity divided by L square. This will be of magnitude this term divided by delta square. So out of 1 and 2, you can easily neglect this term, correct? Because this L square is actually in the denominator. So compared to this L square, this delta square will be much small. So in the denominator, if you have delta square, this total term will be very large actually. So you can actually neglect this term because there is a L square in the denominator and L is very much large. So if L is very much large, this denominator is very much high as compared to this. Clear? So we can actually neglect the first term because this L square, which is having a very large value, is in the denominator. So second is more valuable, correct? Means if you do summation, like this term will contribute to something like 0.0001. this term will contribute something like 10 or 100, something like this. So definitely when you add, you can neglect this. Clear? Which means out of these two terms, if you do some bit of scaling analysis, you will find out the effect of this term will be very, very less as compared to this. Clear? Numerator is same in both. Numerator is same. Okay, numerator is actually same in both the cases. Numerator is actually same in both the cases, but denominator wise it's large. So if you compare, for doing this, did I use anything about flat plate? For doing this analysis, length is, don't feel like this length. Even if you have a curved surface, you can take, even in case of curved surfaces like this, you can take this as your length coordinate. Basically this is your length coordinate at any point. Okay, so basically the stream direction. Okay, so streamline coordinate, you can see this term is actually very large. So this term can be neglected. This term can be neglected. So this term can be neglected. And you can see in boundary layers, because of the same logic between L and delta, dou square by dou x square of any quantity will be very, very less as compared to dou square by dou y square. Maybe you put pressure, velocity, u, v, whatever you keep. This is what it happens. Clear? I think you might have one gate question also on this. I think not in mechanical, but in XC, I guess somewhere. Yeah, first one is negligible. Okay, so this term is negligible. So this is the thing which happens in boundary layers because of this scaling analysis. Clear? Now, come to these terms. These two terms are of same magnitude, correct? You can easily check. If you expand this slightly, if you write this as delta square by L square, you can understand. If you write this term as delta square by L square, then clearly one delta gets cancelled. Then you can see this is u infinity square delta by L square, u infinity square delta by L square. So these two terms are of same magnitude. You cannot neglect one of them. Then this term is of some different magnitude again, u infinity square by delta. Now this term is again kinematic viscosity into u infinity into delta by L by delta square. Okay. Now let us consider certain things. These two terms are of this magnitude, then definitely if you add, the result will also be of this magnitude, correct? Yes or no? These two terms are of this magnitude. So now when you add these two terms, you will get 2 times of this. So if you neglect the constant, then clearly you can see the summation of these two will also give you some term of this order. Correct? Now if you do certain calculations, which is like, let us do inertia force by pressure force. If you do this, for example, inertia force by pressure force, if you do in this case, inertia forces, if you, these are nothing but acceleration terms, so these are inertia terms. So if you see in this case, the acceleration terms are of magnitude u infinity square delta by L square, correct? So magnitude of this will be this, and pressure forces are like, so this term corresponds to pressure force, you have u infinity square by delta, correct? So this is u infinity square by delta. Now if you see this value, u infinity square and u infinity square gets cancelled. This delta which is in the denominator of denominator can be sent to the top. So this expression can be written as delta by L whole square, correct? Yes or no? Type in the chat box. Is this clear to all of you? Did you understand? If you take this inertia effects by pressure effects, because there are now 3 terms in this equation, 1, 2 and 3. One is inertia terms, one is the pressure terms, and one is the viscous terms. So within the boundary layer, if you take this inertia by viscous force, inertia by pressure forces, the magnitude of this ratio, means if you compare the magnitudes of these two, clearly this value is equal to delta by L whole square, correct? And since you know delta is much small than L, this value will tend to 0. Okay? Type in the chat box. Is this clear to all of you till this point? Can you understand? This ratio is coming out to be delta by L whole square, so this value will go to 0. Right? Yes or no? Is this clear to all of you? Please type in the chat box. So if this term is 0, if this ratio is going to 0, very small, if this ratio is going to be very small magnitude, that means out of these two terms, if you compare inertia with pressure, means if you, for example, shift this term to the left hand side and if you compare inertia with pressure, what I can do? Can anyone tell me? Out of inertia forces and pressure forces, I can eliminate one, because you can clearly identify compared to one, the other's magnitude is very, very small. So what is that? Which forces I can eliminate from that equation? Inertia forces or pressure forces? Pressure forces we can eliminate, correct? Because pressure forces we can eliminate, no. Inertia by pressure is 0, no? So what is the meaning of that? What is the meaning of this here? Let us suppose if I write x by y is tending to 0, that means y is very large, na? Correct? Or x should be very small. Did you understand this? Let us suppose if I write a fraction is tending to 0, that means either denominator is very high or numerator is very low. Yes? This is clear? Fraction, simple fraction, okay? Simple bit of, guys, I'm telling you one thing about gate examination. Look, gate examination is like 70% of your subject, 30% of your logic, okay? It's called aptitude exam. You know the full form of GATE, na? Graduate Aptitude Test in Engineering. So majority of the questions you can actually solve with some common understanding, which you generally have in school basics. Understood? I'm telling you guys, pakka, if you bring a nice studying student of 12th class and if you make him attempt GATE exam, pakka he'll qualify GATE exam. My guarantee. I can tell you. Yes. Because I'm telling you, out of 15 marks of aptitude, he can easily solve 10 to 11 marks, because anyone can solve, and that's all there in the school level maths. Correct? In maths, some topics like probability, some basic questions of probability, some basic questions of matrices, some basic questions of calculus, including limits, differentiation, these kind of things, he can easily get some 5 to 6 questions. He can easily solve at least 3 to 4 questions there. So he'll easily get 7 to 8 marks there. Okay? Or maybe let's say only 6 marks he's getting. So 6 plus 11, 17 marks. And from remaining technical questions, easily 4 to 5 questions can be easily solved based on +2 +1 knowledge because of aptitude kind of things, and he can easily qualify 27, 28. He can easily get 30 marks, near to 30. Okay, but many people see GATE as a very complicated exam, and unfortunately, many platforms also show you that GATE is a very this, that, and all. But don't believe all these things. Okay, GATE is a very simple exam. Don't feel very hard about it. Okay. I'm not telling this without qualifying it. I have qualified it 7 times, okay, and I have secured the best rank of All India 10 also. I am telling this after doing all these things. GATE is an easy exam, okay, so don't worry. Clear? सिर्फ आप पे भरोसा रख लो and पढ़ो. That's it. Success के लिए सिर्फ पढ़ना जरूरी है, okay? Not the YouTube sessions, not the things, not that, this and all. Look, there will be thousands of things happening, but at the end of the day, you have to study. बस इतना ही करना है, okay? Chalo, let's continue. So anyway, fraction. So this implies inertia terms are of very, very less magnitude as compared to pressure terms. Okay, that means now there are 2 more terms in this equation, pressure and also this V square. Let us do one more thing. If you do inertia by viscous forces, or viscous forces by inertia you'll do, or viscous forces by pressure forces you can do, because inertia we have already eliminated. So viscous force by pressure force. Okay, now this scales to, what is viscous force? Only this term is remaining, so this is the only term we can take. Okay, so अब GATE 4th year में निकले थे, हाँ 4th year के बाद immediately IIT Madras में admission मिला था, ठीक है? So anyway, here, so if you see that term, kinematic viscosity, U infinity, okay, and delta by 1 delta you can cancel, I think, right? So 1 delta if you cancel, this is 1 by delta L, okay? So this is 1 by delta L, correct? This is what you have, 1 by delta L, okay? And what about pressure force? This is the pressure force, U infinity square by delta, U infinity square by delta, okay? Then you can understand something here. This delta and this delta cancels. This is equal to 1 U infinity also cancel. Then this turns out to be kinematic viscosity divided by U infinity into L. Now, can anyone tell me what is this? What is the term? Kinematic viscosity by U infinity into L. Can anyone tell me what is this term? What is this? You all know what is that term. Tell me. This is actually a ratio. What is that? Reynolds number. Okay. So this is 1 by Reynolds number. Now you know, for delta much less than L, Reynolds number is very high. So that means, understood? If Reynolds number is very large, then definitely that term is actually 0. Clear? So if that term is 0, then again you can see magnitude of viscous forces can be much less than pressure forces. So that means neglect. This is not neglected because of this, okay? The logic is something different. This is neglected because of comparison to this. So which book you suggest us to follow? Just give me 2 minutes. After this I will, okay? So please tell me, is this clear to all of you? Can you understand how by doing scaling analysis we were able to simplify the equations? Yes or no? Yes or no? So please type in the chat box. Clear? Now, if you see all these equations, one thing that you can understand is minus 1 by O dou P by dou Y is 0. Or you can say approximately, because other terms we have neglected. In any boundary layer. Understood? Because in this analysis I have never used anything like flat plate or anything. This L is just the length in the streamline coordinate direction. That's it. Okay. So that's why we can say dou P by dou Y is 0. That means if you take a boundary layer like this, not only on flat plate, on anything. For example, if you say sphere, okay. Let us suppose you are interested in a bit of sphere. Just a minute, guys. I think I have skipped the page. Yeah, here. So you can see, if you have a sphere like this, and let's suppose if some boundary layer is getting developed, if you draw a velocity profile at this point, or if you take any cross stream section, then at this section the pressure at all these points is same. If this is the y direction and this is the streamline coordinate direction, okay, so this is the streamline direction x and this is x dash, for example, which is the tangent at that point, dou P by dou Y is equal to 0. Means pressure will never change in the y direction. So viscous force wala nahi samajh se, look, this viscous force is like here. You can see this got scaled to this term. Okay, now delta 1 delta I have cancelled. So this is like nu u infinity 1 by delta into L. So you can see this term I have written nu u infinity into 1 by delta L, and pressure force is this. So if you do simplification, this turns out to be the magnitude of 1 by Reynolds number. So for high Reynolds number flow, definitely this term goes to 0, and this is what we have. Clear? So that's how pressure will never change in the cross streamline direction. Okay, so pressure remains same at a given section in cross streamline direction. In cross streamline direction, which means one thing you can say, pressure is only function of x. Okay, because normally when there is a boundary layer, definitely if you are dealing in 2D, you know pressure at any point can be depending on x and y. So after doing a bit of scaling analysis, look, this is simple just to make, because some of you may be looking at this for the first time, so I have done very slowly. Otherwise, writing these magnitudes and taking this will take hardly 3-4 minutes, 2-3 minutes maximum. Okay, but anyway, so you can understand dou P by dou Y is 0, means along the cross streamline coordinate, definitely the pressure variation is 0. Clear? Are you all clear with this or not? Please tell me. I know things are very much easy. Okay, nothing complicated here. Only divisions and multiplications is what I have done. Okay. Yes or no? So tell me, yes or no? Anything? Nothing? Okay, clear. Good. Let's continue. So yeah, we identified purchase function of x. So this is only in y direction we have done. Okay. So if you do use the same parameters for the x direction, let us see what happens. Okay. So in x direction, I want you to show something. In x direction, guys, I'm repeating again and again. I don't mean x as literally the flat plate x coordinate direction. X is of any direction. Okay, means basically along the streamline direction. Y is the cross streamline direction. It can be flat plate, sphere, cylinder, whatever. Okay, that's why I have written for any external in any boundary layer. Clear? Now, anyway, let's see here in x direction. If you write u into dou u by dou x, because unsteady terms we have neglected, v into dou u by dou y, correct, right? U into dou u by dou x. Yeah, this is equal to minus 1 by rho dou p by dou x plus nu times of dou square u by dou x square plus dou square u by dou y square. Now clearly in this summation you can neglect this. This term you can neglect because of the same logic what I have shown in the y coordinate direction. Okay, so this term you can neglect because no, I haven't done PhD, I have to opt out of it. Okay, so you can see dou square by dou x square, dou square by dou x square is actually very much less as compared to dou square by dou y square term. Clear? Okay, because of that same logic I am neglecting this term. Now coming to this, guys, this magnitude, if you check, magnitude of these two terms will come same. You can see u can be scaled to u infinity, this dou u can be scaled to u infinity, this can be scaled to L, this can be scaled to u infinity y by delta by L into u can be scaled to u infinity, this can be scaled to delta, so delta delta gets cancelled, this will also to scale to u infinity square by L, this also scales to u infinity square by L. So these two magnitudes are almost of same order. You cannot neglect any one of this summation. Now let us, if you see inertia, pressure and viscous, you will find an interesting thing. You cannot eliminate any of them. Okay, nothing will come as delta by L like you have got in the y direction, and also nothing will come out as 1 by Reynolds number also. Okay, so normally will you do that as an exercise? Like I'll give you the terms. This can be scaled to u infinity square by L, and this can be scaled to nu u is there, so u infinity by delta square. So you can understand that if you do this scaling, this is u infinity square by L, this is u infinity square by L, this is nu u infinity by delta square. You may feel because of this delta square the value can be much small as compared to this, but one thing, you don't have square in the top, and also you have kinematic viscosity division, so you can see nothing you can eliminate. Like clearly these three terms are of same order. If you do this analysis a bit, you will understand this term also cannot be eliminated, because you can, I may show you actually. If you do inertia, no, this is viscous, right? Viscous force by, or inertia force by viscous force, for example, let us take, because inertia or pressure both are of same scale, you can take anything. If you do this, for example, this scales to inertia force. Okay, so inertia is this guy, u infinity square by L divided by pressure. This we want to calculate viscous force, right? So viscous. So viscous force is of scaling u nu u infinity by delta square. Okay, so if you simplify this, you can say u infinity, this gets cancelled, and this is equal to u infinity delta square by nu times L actually. Okay, you will understand after a bit of analysis that this is connected to Reynolds number, but you cannot neglect this expression. Understood? Because I'm telling you, you may feel delta is very small, but practically kinematic viscosities are also very small. Okay, so you cannot neglect this term. Understood? You cannot say, like we have said in the y coordinate direction, that this term is large, this term is small. Like this you cannot go in this case. That's why you cannot eliminate any of the remaining terms. Okay, therefore you can see after a bit of understanding in scaling, you can talk something like, what is this? Okay, this is not needed anyway, just to explain you I have taken. Now boundary layer equations. Boundary layer equations. Guys, before writing boundary layer equations, I want to tell you one thing. This term can be written as dp by dx, because you know clearly in the cross streamline coordinate it won't change, so p is only function of x. Dou p by dou x can be written as dp by dx. One important point I want to guess, this I hope you have understood, you cannot neglect actually. Then try to understand something. Let us suppose if I give you the help of some example, for example, I'm just geometry wise I'm showing it using flat plate. This is X, delta versus X. Now clearly, you know, in this region viscous effects are very high, so this is viscid region. You can actually divide the complete flow into two regions, viscid region, this is inviscid. Of course here also you have viscosity, but the effect of shear stress is very less. So whenever you can take this as inviscid region, in this region you can apply Bernoullis. Bernoullis is valid. Again, depending upon the type of flow, you can actually decide whether you have to apply on the same streamline or on different streamlines. Here Bernoullis is not valid. Okay, Bernoullis is not valid because the first assumption that we make in Bernoullis is the flow is inviscid. We never considered viscous forces, but in this region you cannot neglect viscous forces. Okay, because they are still there. You cannot neglect this term. Right? In y direction you can neglect, but in x you cannot do this. Okay, so that's what you have. Right? So Bernoullis equation is not valid in that region. Now you can see, actually on the diagram for some different cause. Okay, I'll draw one more. Now try to understand. For example, I'll explain you in this coordinates. You can understand. This is x, this is y. Okay. Now if you take a section, for example, like this. If you take a section like this, tell me one thing. You know there is no pressure difference here along these points. Pressure is same at all these points. Similarly, that means, can you tell me what, and here the flow is only in this direction. It's going at u infinity in the stream direction. Okay, this x is basically the stream direction. So if x is stream direction, clearly you can see normally from your Bernoullis equations and all, you can identify this pressure remains same here. That means overall there is no pressure gradient in the y direction. That means whatever is the pressure variation here in the terms of x, same pressure gradient will also get imposed in this boundary layer. Yes or no? I'm repeating this statement. See carefully. You know outside this the flow is in one dimensional, it's u infinity, means along the stream direction. Then along perpendicular to the stream direction, since there is no velocity in the perpendicular to the stream direction, pressure actually remains constant along this. And also, you know, at this point there should be definitely continuity. Okay, so at this point it should be continuous. So the pressure is constant till this point, the pressure is also constant till this point, and here it should be continuous. So the pressure at any given coordinate of y is same at a given x. But if you take two sections like this, if you take two sections like this, outside you can understand one thing. The pressure at this section and the pressure at this section is equal only for flat plate, not for other geometries. Like for example, I'll show you. See here. If you take a cylinder, normally I don't know whether you might have seen in kinematics, but anyway in potential flows I'll teach you. So if you take a flow in this direction, for example, you can understand the velocity at this point and this point, even though the boundary layer is something like this. Maybe the boundary layer could be something like this. This is boundary layer. This is outer boundary layer. Like here there is no viscous effects, inviscid. Even though this is inviscid region, you can clearly understand the velocity at this point and this point will not be same. You can do this with the help of a simple kinematics analysis. The I think in polar coordinates I have to teach, but in potential flows I'll teach this. Okay, you can understand clearly here some stagnation points will come. I mean very close to this. Okay, let us suppose if this distance is very small. Okay, then definitely stagnation point, then definitely velocity keeps increasing. Okay, so even outer boundary layer, the velocity at these 2 points need not be same. Yes or no? Is this clear? Stagnation occurs. Yes, of course. From stagnation again the velocity keeps increasing. Can you understand this? Which means my intention is to tell you in flow over in external flows, actually the velocity in the outer flow region, means outer boundary layer region, need not be constant. It is constant only in case of flat plate, but in general if you go for generic examples it need not be constant. Clear? Is this clear to all of you? Come on guys, type. It's 8:40 already. I thought of finishing this topic by 8:30, but anyway, please tell me. This can happen, right? Now, but one thing you can always say in this inviscid region, P infinity, let us suppose if the outside stream pressure is P infinity plus half U infinity square rho U in inviscid region or outer the boundary layer region, basically that's inviscid. What you can say is outside pressure by rho plus U infinity square by 2 is always a constant, correct? And this is the streamline coordinate. This is x in this direction. Now you can see if this is p infinity by o, u infinity square by 2 is constant. I am dropping out the potential term, no variation with respect to z and all. So if you differentiate this, if you take this guy as incompressible, then you can see dp infinity by d rho by dx. Okay, so 1 by o if you take constant, for example, dp infinity by dx plus half into 2u infinity into du infinity by dx is equal to derivative of constant is 0. These guys gets cancelled. So 1 minus 1 by o dp by dx. Infinity is basically the symbol to denote outer flow. Okay, so this is equal to u infinity into du infinity by dx, which is the variation of free stream velocity in the streamline coordinates, which is need not be 0 for cases like this. Clear? For cases like this, this quantity is not 0 because along the stream direction, these velocities at different points can be different. They are not same. But for flat plate, special case. So why I am telling you this is, see, why I am telling you this, you know, when you are writing boundary layer equations, your continuity equation can come something like dou u by dou x plus dou v by dou y is equal to 0, and momentum equation gets converted to u into dou u by dou x plus v into dou u by dou y is equal to minus 1 by o dou p by dou x. That minus 1 by o dou p by dou x I can write as u infinity into du infinity by dx. You may ask me, how can you say this is outer boundary layer, but the pressure what we are writing is inside the boundary layer? So how can we say both are equal? Because of this. I mean, because of this explanation and this equation. Understood? Because of this equation, what happens here at a particular x, same happens here inside. Understood? Because of that continuity, I can write this pressure, which is actually related to the outside boundary layer, can be same as the inside, which means what is the pressure gradient that comes outside the flow, same pressure gradient will be imposed inside the boundary layer. Clear? Because of dou p by dou y is 0 for any boundary layers. Clear? Now this quantity can be replaced with this u infinity into du infinity by dx plus nu times of dou square u by dou y square. These are the two equations which we write for the boundary layers. You may ask me why you did not write the y momentum equation. Because I have actually written the y momentum equation. If I don't use the y momentum equation dou p by dou y is equal to 0, I cannot replace this term. Understood? So writing these terms in terms of u infinity or maybe minus 1 by o dp by dx tells you that dou p by dou y is actually 0, which is a consequence of y directional momentum equation. So generally when you ask people to write boundary layer equations, they write only these two equations. Clear? Because writing this equation will automatically include, when you write minus 1 by o dp by dx, why you are writing dp by dx? Because you know dou p by dou y is 0. That's why the second equation will actually imply in the first equation. Got it? Okay? Is this clear to all of you? So anyway, this is the equation. Now, special case. For a flat plate, okay, for a flat plate, du infinity by dx. What is this value? What is that value for a flat plate? Like for example, you see, if you have a flat plate like this, or like this, or like this, for example, outside the boundary layer, this is u infinity. So what is du infinity by dx for a flat plate outside the boundary layer? In a far field, not in the boundary layer, somewhere long away. What is that value for a flat plate? Can anyone tell me what is the value of free stream velocity gradient in case of flat plate? Think just a bit. Like I have told you one case. In this case, the velocities are not same because you have certain kinematics that's going on. If you take a flat plate, for example, like in this case, at every point on this outer flow field, what is the fluid velocity? Can you tell me? at every point on the flow field, outer flow field, outer the boundary layer, at every point in this region, what is u infinity? U infinity is constant, correct? Yeah, u infinity is constant in this case of flat plate. If u infinity is constant, what is this term? What is this term? What is this term? 0, right? Because this guy is constant, so derivative is 0. This means in the beginning someone has asked me what is pressure, how pressure changes. This is what you have to understand to know how pressure changes. Okay, for flat plate, pressure is constant all over, which is one of your gate question again. Okay, so P is actually constant in case of flat plate, only flat plate. Okay, if it's cylinder or sphere, this is not 0, so this will not be 0. Okay, clear? Can you all understand this? Because many times you might have read pressure is constant in a boundary layer, but why? This is the answer. Okay, is this clear to all of you now? In case of a flat plate boundary layer, normally in case of boundary layers, you can have this. So did you design test series of FM? No, I am not taking. I think Shivam Sai is doing for FM. I am doing for maths and applied thermodynamics. Yeah. But is this clear to all of you? Please type in the chat box here. Did you understand something or not? If you don't understand anything, just make sure these are the equations for boundary layer equations. Okay. With the help of which you can actually, yes, basically no pressure changes outside the boundary layer because no velocity changes. Okay. Now, so what happened? These things are clear. So pressure is constant, then velocities we identified. What we can do? So next, so this bit of scaling is really important here. That's it. Okay, so some bit of scaling can actually give you. I told you one more thing, that I'll show you delta by L. Mathematically, if delta is very less than L, this implies Reynolds number is very high. Correct? This is what I told. I'll show you. Now, clearly you cannot neglect these things in y, not in y, in x direction, in x momentum equations. You can see you cannot neglect any of these terms. But one thing that you know is this magnitude and this magnitude scales equally. Okay, so this implies u infinity square by L scales to nu u infinity by delta square. Okay, because you cannot eliminate anything. Okay, so when you cannot eliminate anything, this is what you have. So then one u infinity gets cancelled. This implies u infinity, or you can see delta square. Okay, so delta square, if you bring here, delta square scales to nu infinity L by u infinity is what you have here. Correct? So delta square will scale to nu L u infinity. Let's do one thing. If you write a square here and if you put a L here, you can do this. If you bring this delta L square to the left hand side, delta by L whole square will actually scale to, if you bring this L square here, you have kinematic viscosity by u infinity into L. This is what you have. Okay, and clearly you know delta by L is scales to 1 by root Reynolds number, and you can understand actually from this delta scales to L by root Reynolds number. This is what you will get. See how beautiful scaling analysis is. Without doing any bit of solving of the equations, you can say if you delete this sign, this is equal to some constant. That's it. So delta is equal to some constant times L by root IL is what you will get after you solve this. Momentum equation. Okay, sorry. Where did I get mom? momentum equation. Momentum equation. Look, without actually solving any equations, you came to know in a boundary layers pressure don't change in the cross stream direction. In case of a flat plate, pressure is constant everywhere. You came to know as x increases, delta increases. As x increases, tau w decreases. You also came to know that delta will be of this form. So if you put some constant, that's it. Constant times L by square root of REL is what you'll get. Without, so that's the power of scaling analysis. Without actually solving the equations, it's, you know, if you want to solve this equation, you know, it's really tough. You cannot even solve this equation completely. But without any solving, just by understanding certain magnitudes, by eliminating some terms, you found out this delta will actually come to this form. And we all know actually practically delta is equal to some constant times x by root Rex. Correct? So if you delete this guy, this delta is of the order this, which is this from scaling. Did that make sense? Understood something? Fine. So now let's talk about the boring and common stuff, which is displacement thickness, momentum thickness, energy thickness, all these things. Okay, which you generally know. Do you all know the expressions directly? Then yeah, here. Okay, so let's see certain important parameters which are important in understanding drag forces. Why actually calculate this kinematic thickness, dynamic thickness, all the things is practically you can see this is like this is like for calculating drag forces. The main effect what you have to do is you have to calculate what is drag force, correct? Then to calculate this drag force, first of all you should know, let us suppose if some fluid is flowing here and there is a sphere, okay, or let us suppose if there is some fluid and this body is moving, then in that case if you want to calculate the effect of this fluid, you should calculate all the drag force shear stress at these points, correct? You should know what is the shear stress due to the fluid at all the points on the wall, correct? So there should be some technique to calculate. Good morning, Dharmendra. So if you see this is sphere, actually if you want to calculate what is the drag force acting by the fluid on that objects, you should know what's happening at the point of contact, means what are the wall shear stresses at all the locations, correct? Now to calculate wall shear stresses, we have actually two people. One command has actually given one equation, which is the momentum integral equation. Okay, so in calculating the momentum integral equation, we have to talk about certain things like displacement thickness, momentum thickness, and also energy thickness is also sometimes important. We will see what's energy thickness also. Okay, now let us see what's this momentum. No, first we'll see displacement thickness. Displacement thickness, which is normally denoted with the delta 1 in general. I think delta star you keep, right? Yeah, delta star. Let us see, this is displacement thickness, which is delta star. Now what is this delta star in actually, why it's called displacement thickness is actually formula you all know, right? Even I think x and y directions. So let us say at this point this is delta, for example, at some location x, this is delta. You know, x is not constant, that goes up. Okay, then yeah, I understand. Super morning time the attendance is slightly less because super 1500 is parallelly going. I think Apupsa is taking some, right? Yeah. Okay, so fine. Anyway, you can watch this. So if this is delta, why it's called displacement thickness? Okay, so formula wise, you know, if the velocity at any point, if this is free stream velocity u infinity and here it is u at any location, then for a given function u by u infinity is equal to some function of eta, okay, where eta is a non-dimensional variable, y by delta actually. Okay, so eta is y by delta. You will have some function of y by delta. Okay, you can do integrations. So practically this delta star is given by integral 0 to delta 1 minus u by u infinity dy. Okay, now what is this guy, what is this integration and why we are doing it? Okay, doing it is simple. It's a single variable integration. You'll have only one variable y and you have to integrate. Okay, single variable, one variable integration you can do. But what is this equation actually? Why it's called displacement thickness? I told you in the beginning of the session that the streamlines will actually get diverged, correct? I have shown you this. The streamlines will actually get diverged. Now, let us suppose if the plate is not there, this fluid layer might have, this fluid layer might have traveled like this, yes or no? So this is streamline in absence of fluid layer, in absence of plate, in absence of plate. Now the actual streamline, which is supposed to be like this, got displaced, yes or no? So this streamline, this is the displaced streamline because of the plate. This is the displaced streamline because of the plate. Did you understand? Basically all streamlines will actually all streamlines will actually diverge. Okay. Now whenever there is no plate, this streamline would have actually gone straight, but because of the presence of the plate, the streamline has actually got diverted. Okay. Now at that point where you reach u infinity, look, from this point, if you travel in this direction, then clearly as y increases, your velocity will increase. At some point you will touch u infinity. Let us suppose if this is the boundary layer which I have drawn. Once again I'll draw. It got erased. This is delta versus x. Okay. At this point, at this section, you will reach free stream velocity, very close to free stream velocity, 99.99 whatever. So you will reach close to free stream velocity. So at that point, the displacement of the streamline is nothing but delta star. Displacement thickness is the thickness by which the streamline at free stream velocity gets displaced. Understood? That's why it's called displacement thickness. I'm repeating, the thickness by which the streamline of free stream velocity gets displaced at a given section is called delta dash. And what is the importance of this delta dash? Delta dash practically signifies the loss in flow due to presence of the plate. At a section. Clear? So if there is no plate, within the same section some amount of mass might have gone, but because of the presence of the plate, these streamlines has got diverted, and to this same section now comparatively less amount of mass will flow. So the gap between those is actually compensated by this delta star. Okay. What is the loss in momentum at this? If you see in this layer, actual mass that would have flown is dm dot, which is equal to rho u infinity, or right now if you see, this is like rho u infinity into dy into w is what the actual mass which would have flown to some small elemental distance. But now because of this plate, what is the actual thing which is flowing? This is ideal when there is no plate. To some section, if you take a small segment dy and if you do to that element, this is the mass flow which would have flown. Okay. But what is the actual mass which is flowing now? Because of the presence of the plate, velocity gets changed. So u dy into w, actually w is width of the plate. Width of plate. Therefore, what is loss in the mass flow at that section? M dot d m dot loss is equal to difference between these two. So rho w dy into u infinity minus u, actually. Okay. So this is the loss in the mass flow rate. Can we understand it like boundary thickness but shifting bottom layer of u infinity? Maybe. Yeah. Basically we are calculating thickness of the streamline without plate. Yes. Without the plate, what is the streamline thickness? It's same like if you move the plate like this without the effect of this viscous effects, then this distance. You can even understand that. Okay. Now this is u infinity minus u. Now what this delta star is, that delta star actually compensates for the loss in the fluid. Okay. So this mass flow rate which is actually lost is equal to, so the total mass which is lost is like integral 0 to delta, because the section is of height 0 to delta, because y can actually change from 0 to delta at any given section. So 0 to delta, this term is actually equal to the mass which is flowing through this, because this is the mass flow rate which is lost because of the plate. So that excess mass we are considering to compensate the loss here is nothing but delta star into w. So this is the flow area. At every point in delta star, fluid moves with u infinity velocity. Okay, and density, of course, mass flow rate we are writing, so density should also be there. So density is what you have, clear? So this is the mass flow rate which is passing through this section, okay, which I have done in blue color, clear? So at every point the flow velocity is u infinity because this is outside boundary layer. So this is what you have. If you simplify, you can clearly get this expression with a one step, that's it, okay, nothing big. So if you cancel this density width, then definitely if you bring this u infinity here, delta star is equal to integral 0 to delta 1 minus u by u infinity dy, that's it. Okay, so this is the equation which is delta star. Did you understand what is displacement thickness and how it's calculated? It's a one line compensation for the loss in mass. Okay, did you understand this? This is the actual when there is no plate, this is the real, this is the ideal when there is no plate, this is the actual. Difference between those two is the loss. Loss is compensated by this. That's it. These are very basic stuff you can understand. And this integration you can do very easily. Okay, it's a single variable integration. You can do very easily. Okay. Now, similarly, you can talk about momentum, thickness, which compensates for loss in momentum again. So theta is what you generally denote this. So theta is integral 0 to delta momentum u into u minus u infinity. So u by u infinity into this corresponds, this u corresponds to mass flow. So loss in momentum u infinity minus u. So 1 minus u by u infinity dy. Correct? I hope this is correct. Yeah. This is for the momentum thickness. Okay. Similarly for kinetic energy, what you can do? Kinetic energy thickness. If you simplify, this equation is same. Instead of considering mass, you should consider momentum in the momentum thickness, energy in the energy thickness. That's it. Okay. So kinetic energy thickness delta double star. So this is equal to, so this u will remain same because of the mass flow multiplication, and kinetic energy. So kinetic energy is half mv square. So square will be there. Okay. So u by u infinity into 1 minus u by u infinity, u square by u infinity square dy. That's it. Because here it is momentum, so only one u. Here it's kinetic energy, so half mv square. So this gets cancelled. Why momentum thickness? I'll tell you. Good question. Why momentum thickness? I have to answer definitely. It's my responsibility. I have to say. Are you all clear till this? These are very simple equations. Okay, within one line you can get these equations. Like how you got here. Okay. I think some of you are thinking, sir, हमको boundary layers में ये इक्वेशंस बहुत आसान से आता है, जो क्वेश्चंस इससे आता है बाउंड्री लेयर थिकनेस, मोमेंटम थिकनेस, काइनेटिक एनर्जी थिकनेस, वो क्वेश्चंस ही हम सॉल्व करते हैं. आप बोलते हैं कि ये बहुत सिंपल स्टफ एंड इजी स्टफ. So what is the, now I'm feeling that I don't know anything in boundary layers. Is that what you are thinking? How many of you are feeling this? हमको सिर्फ ये इंटीग्रेशन करने ही आता है, उससे बिना कुछ भी नहीं आता बाउंड्री लेयर्स पे, एंड आप बोल रहे हैं कि so these are very basic and simple stuff, nothing much. Is that what you are thinking? How many of you are thinking this? I know definitely there will be some people who think this, right? But actually, yeah, गेट में बहुत सारे क्वेश्चंस आते हैं इसमें. Okay, so इंटीग्रेशन करना आना पड़ेगा. You just have to know integration, and I hope you all know how to do single variable integration. Okay, one variable integration. Okay, guys, I suddenly remembered integration. I think so much of boundary layers I'm teaching. Shall I do one maths question? Because in Telegram group, someone has asked me yesterday. There is a question e power sin x by e power cos x. They're asking you what is the maximum value. Like there is a function. Actually, in Telegram, someone has asked me yesterday. F of x is e power sin x by e power cos x. So how to calculate the maximum value of this? This is what I think. The question, right? This is the question, I think. Is that the guy who asked me this in the live? No. How to calculate the maximum of this function? Shall we solve this? Just 2 minutes, I think we can need. Okay. Now see here. It's a very simple question again. Basically, this can be written as e power sin x minus cos x. Okay, so this can be written as e power sin x minus cos x. Because e is a constant, e is a positive constant, of course. If you want the maximum value of this, you have to calculate what is the maximum value of this. Correct? x at maximum of f of x is same as x at sin x minus at maximum of sin x minus cos x. This is what you know, correct? Now this is a function first order. If you do the first order differentiation, if you do the first order, I'll explain it in two ways, but one is very shorter way of that. Okay, so normally if you want to calculate maximum of sin x minus cos x, then clearly you do the first derivative equal to 0, cos x plus sin x is equal to 0, so tan x is equal to minus 1. Okay, so tan x is equal to minus 1, right? So if you solve this equation, then clearly you'll get x is equal to minus pi by 4 comma 3 pi by 4, at least in the first cycle roots. Now clearly if you do the second derivative test and all, you do certain substitutions, clearly you will identify if you put this 3 pi by 4, then definitely these things will become the maximum value will become root 2. Okay, clearly you do the second derivative test. If you put minus pi by 4 and 3 pi by 4, and clearly you will see that the second derivative at 3 pi by 4 will become positive, I mean it become negative. Okay, and definitely this is the point of maximum. So if you put 3 pi by 4 here, this is 1 by root 2 minus this is minus 1 by root 2, so this is actually square root of 2, so square root of 2 is the maximum value of this. Okay, so therefore the maximum value of this is e power root 2. But without doing all this business, I can just tell you one, this is the classical procedure, you know, correct? You all know this. Equating the first derivative to 0, then get the stationary points, substitute the stationary points in the second derivative. If the second derivative is negative, the function is having maximum. If the second derivative is positive, then the function is having minimum. Then definitely you can calculate what is the maximum and minimum values of this function. Okay, but especially for these forms, sin x minus cos x, sin x plus cos x, whenever they give you certain things, I'll just tell you one thing. I'll give you one small technique which you can understand very easily. Normally if you have anything like a sin x plus b cos x plus c, you know, after doing the differentiation analysis, you found out the maximum value is root 2, which is basically root 2 is the maximum value of this function. Okay, so for any function of this form, range is c minus root of a square plus b square, c plus root of a square plus b square. Means the minimum value of this function is going to be this, and the maximum value of this function is going to be this, and whatever may be the values of x you keep, the values of this function will come something between these two. Okay, it's very easy to show. You can see this can be written as c plus a sin x plus b cos x, correct? Now what I can do is, look, okay, then if you make a triangle, this is a root of a square plus b square, then definitely this is going to be b. Okay, because a b root of a square plus b square, and this is a right angle triangle. Then this can be written as some cos alpha or sin alpha or maybe cos alpha. Okay, you can take this as a and this as b, for example. Even you can do whatever, a and b. Then this is cos alpha, then definitely this is going to be sin alpha of that triangle. Okay, so the total expression gets converted to c plus root of a square plus b square cos a sin b plus sin a cos b. This is something like sin alpha plus x. Okay, now this is the same function as this. Okay, now if this and this are same, whatever you keep in place of x, this value cannot go beyond 1. Yes or no? For this function to be maximum, c is constant, a, b are constants. So if you want to have maximum of this function, then clearly this function has to be maximum. Whatever you keep in place of alpha and x, sin cannot go beyond 1. Okay, so the maximum value comes when sin is 1. So c plus root of a square plus b square is the maximum. Similarly, whatever you do here, this cannot go beyond minus 1. So minus 1 is the minimum value of this. So when you put minus 1, this sign will change. This. Okay, only for this function. Then means of any function of this category. Now if you see here, c is equal to 0, a is equal to 1, b is equal to minus 1. So max value is c is 0, 1, minus 1. Okay, if you know this, then it's very simple to solve. Basically the maximum value of this is this. If you know this, solving this question will take only 10 seconds or 15 seconds maximum. Tan and cot you cannot do, okay, because tan and cot are not finite functions. That's why in exam also they'll focus only on sin and cos to save you time. But if you don't know this, you'll be calculating derivatives, all the stuff you'll do. Okay. Normally in maths you have a lot of techniques. Okay, so like if you are doing mean value theorem, Solis theorem, they can or if you're doing these numerical methods, there are plenty of techniques where people, if you don't know those points, they're not techniques actually, conceptually some strong points. If you don't, this is not a technique, okay, it's a bit of workout here, okay. So if you know these points, then definitely questions can be solved very easily, okay. I'm telling you, in GATE examination, if your concept is strong, solution size will decrease, Paka. Okay, so anyway, this is not a bit of our story right now. Okay, fine. Now let us see some other things. How to calculate the drag force? That's the main point of interest for us, okay. If you have this plate like this, okay, so if you have this plate like this, then if this is delta versus x, how to get this wall shear stress at different point? It decreases with x, but how come? Because if you want to calculate drag force, that should be there. Now, how to calculate the drag force? We see von-Karman's momentum integral equation. Momentum integral equation. So if you see this, we actually get tau w by rho is equal to u infinity square d theta by dx plus u infinity du infinity by dx into into 2 times of delta star plus theta. This is what we'll have actually, okay. So this is the von-Karman's momentum integral equation actually. But in case of flat plate, right now in GATE syllabus also I think only flat plate is there. For flat plate, this is how the equation gets reduced actually, okay. So this is the flat plate because this guy is 0 here in this case. Now we can actually see this very simple again, only spending just some 5 minutes can actually tell you this. Look how we can see that. This is delta versus x. So since tau w changes from point to point, let us take a small section, okay. So if you take a small section like this, of fluid, for example, say points A, B, C, D, and this is boundary layer, okay, and this is the flat plate, I mean the layer at the contact of the plate. Now clearly fluid goes like this, it comes out like this. Some fluid also enters from here because the top face here, the fluid velocity at every point is u infinity, so that also comes in, okay. Now if you do momentum balance, for example, first of all, if you write mass balance, mass conservation, mass flow rate to AB plus mass flow rate to BC, no, not BC, AC should be equal to mass flow rate to CD, AB, AC, so CD, because nothing can come through here because this is a fixed solid boundary, okay. Then if you separate that, look, I am just elaborating it so that you can understand. Okay, now one thing that you know is when fluid flow in this direction, it will try to pull the plate in that direction. So clearly plate will exert a reverse force. Means, for example, if you see, if this is tau w which is acting, then this is actually the force which acts in the reverse direction on the fluid, correct? So on the fluid, so this is the external force acting on the fluid, which is tau w into, let us say thickness is b, for example, b dx. If this length is dx, if this is dx and this is at a distance x, for example, then if the width of the plate is b, then b into dx is the area. Like if you take a 2D, you can understand, see here, if you take a 2D, for example, this is like this area, okay. So this thickness is b and this is dx, okay. So this is the area. So for that area, for the volume of the fluid above that, we are applying the control volume. So first thing that you know is mass balance, m dot ab plus m dot ac is equal to m dot cd, okay. And clearly this is delta and this is also delta because this dx is very small. So let us say that's also m dot ab can be written as integral 0 to delta rho u b dy, right, plus m dot ac, we don't know what is m dot ac, still m dot cd can be written as integral, m dot cd can actually be written as m dot ab plus dou by dou x of m dot ab dx, because this is, again I told you how this comes, linear approximation of Taylor series. So m dot ab plus dou by dou x of m dot ab times dx, which actually passes because the section will have a difference of dx. This thickness is dx, okay. So this thickness is dx. So this is actually equal to m dot ab, so integral 0 to delta rho u b dy plus dou by dou x of integral 0 to delta rho u b dy into dx. Now clearly these two guys lift off, okay. So mass flowed to AC, the mass which is entering through the phase AC is dou by dou x integral 0 to delta rho u b dy times dx is what we have. Is this clear to all of you till this? Mass balance, only 2-3 steps, that's it, simple mass balance. Is it clear? If it's clear, then I'll write momentum balance, you can see the equation, okay. So please type in the chat box, is this clear to all of you? Yes or no? Please type in the chat box. Yes? Now, okay, let's see the momentum equation. Momentum equation. So this is mass balance basically, okay. So this is mass. Now in case of momentum, this is the control volume, okay. So if you take this guy as the control volume of the fluid, now on this control volume, this is the external force acted by the plate on the fluid, correct. So this is external force, so minus tau w into b dx is equal to, we know, we have seen momentum sigma f is equal to m dot v out, m dot v in relative, okay, because this is anyhow in fixed, plate is in fixed condition. So minus tau dot b dx is the reverse force which is acted upon by the plate on the fluid, correct. So this is equal to momentum leaving out m dot cd into u, so that can be written as integral 0 to delta rho u square b dy, because this is the mass flow rate, but if you are considering momentum to this mass, you have to multiply one more u inside, yes or no? Can you get this? So into u. Did you understand? This is only for mass. So if you want momentum, you have to multiply one more u. That's what I'm doing it here right now, okay. Anyway, that's the mass equation. So here, that's why this u square is coming, plus dou by dou x of integral 0 to delta rho u square b dy dx. So this is the momentum which is leaving through this phase CD, okay. Is this clear to all of you? Yes or no? Please type in the chat box. Is this expression clear? This is the momentum which is leaving through this phase CD. Now let us subtract these two things, mass which are coming in. M dot AB. M dot AB is integral 0 to delta. M dot AB is like integral 0 to delta rho u square b dy minus integral m dot AC into C. So try to understand one thing. Flow also comes through this phase AC, but can anyone tell me all the particles which enter, what are the velocities they have before entering at this interface? Can anyone tell me? If fluid is entering like this, can anyone tell me at all these points the particles will enter at a velocity which is, what's the velocity of all the particles which are coming inside at this interface, at the control surface, when they're crossing the control surface, what is the velocity of these particles? u infinity, correct? Because here it is u infinity completely outside, so it is u infinity. Okay, so if this is u infinity, the momentum which is coming to AC is nothing but m dot AC. So m dot AC is this. So dou by dou x of integral 0 to delta rho u b dy dx, and actually should multiply u infinity inside because this mass will come at a velocity u infinity. So you can write this u infinity outside also because it's a constant. Is this equation clear? This is the momentum equation for this control volume. If this is clear, that's it. Simplifying this will give you the equation, one command momentum integral equation. But is this clear to all of you? Okay, please tell me, is this equation clear to all of you? Just I have written the momentum balance, that's it, nothing big I have done. Yes, now let us simplify this. Now this term and this term will get lifted off. Then after we have a minus sign, so let's take one more, and I think b you can cancel in all the terms. Okay, b you can cancel because b is constant, which is in every term. So this implies minus tau w, dx is also there, right? This dx is also multiplication in every term, so we can cancel this dx also. Dx, dx and dx can get cancelled in all terms. So we have minus tau w is equal to, this term went, so dou by dou x of, this is also dou by dou x, limits are same, so we can write as a single term, dou by dou x of integral 0 to delta, here you have rho u square, here you have rho u into capital U. Okay, so rho u square minus rho u infinity dy, this is what you have. Okay, now density is also there, constant. So what we'll do, we'll take out this density from here and we'll put it here. Using this minus sign, we'll put a minus here and plus here. So this gives you tau w by rho is equal to, now density went, so you have dou by dou x of integral 0 to delta u infinity minus u square dy. Okay, now what we can do, we can actually take one u out, and let us suppose if we divide with u infinity square, this equation gives you tau w by rho is equal to, if you do a u infinity square multiplication, this can give you 0 to delta u infinity by u infinity square minus u square by u infinity square dy. Okay, I'm just adjusting a u infinity square and u infinity square here. So this gives you tau w by rho is u infinity square times dou by dou x into, then if you take one u by u infinity out, we have integral 0 to delta u by u infinity. So if you take u by u infinity out, 1 minus u by u infinity dy, that's it. This is simply maths, but actual fluid mechanics is here. Okay, that's what. Then after, so that's it, this is theta, right? So this is your theta, so this gives you tau w by rho is equal to u infinity square d theta by dx. I'm writing x because you see delta depends only on x. Okay, so this partial I can convert to exact. So this is for flat plate. For flat plate. So this is for flat plate, which I have shown you 2 slides before here. So this is the equation. Okay, simple mass and momentum balance, that's it. Okay, actually derivation got finished here in this one page. This is mass, this is momentum, but you have to simplify this because if it is in this way, you cannot understand much. So bit of simplification leads to some simple terms. Okay, is that clear to all of you? Did you understand this? Are you all understanding boundary layers? What's happening here? So wall shear stress at any point is function of density u infinity square d theta by dx. Okay, I'll just tell you one important point here. For velocity profile, let us suppose if they define f as this, u by u infinity is equal to 2 times of y by delta minus y by delta whole square. Actually, you know, 2 eta minus eta square is what we have. Why this particular profile is important, I'll just tell you. So why this is important, look, for a flat plate, normally if you do the analysis only for flat plates right now, guys, actually I want you to tell one thing. Very loosely we can say that at x equal to 0 means, for example, if this is x coordinate, if this is x and this guy is y, you generally say loosely that at x equal to 0 delta is also 0 because you know the flow actually starts.
but exactly at x equal to 0, it's a point of singularity. Okay, if you put x equal to 0, you won't get mathematically any value. Okay, if you go mathematically, you will understand exactly at x equal to 0, you cannot write delta equal to 0. But what we do is, generally, since in the right limits it is very less, we loosely write at x equal to 0, delta is equal to 0. Okay, in general. But practically at x equal to 0, mathematically, whatever the boundary layer analysis you are doing, that gives a singularity. Okay, but anyway, you can check later. Why this is important is, look, we have three boundary conditions at any point. Look, at y is equal to 0, what is u? 0. We know this. Why? No slip. Correct? No slip. Let's log this guy. Okay. At y is equal to delta at any cross section, what is u? U infinity. Correct? Very close. So we can write to u infinity, because let us say delta is that location where we are reaching with very less error, only 1 to 2% difference. At y is equal to delta, you can also have dou u by dou y is equal to 0. Correct? Because at this point u is the maximum velocity. So at maximum velocity, if you differentiate this, dou u by dou y is 0. Right? Because velocity keeps increasing, it gets maximum here. So at maximum point, the first derivative with respect to y has to be 0. So these are the three boundary conditions which you have generally in common. Okay. Now using three boundary conditions, maximum how many constants you can evaluate? Tell me. Let us suppose if I express as a polynomial function. For example, if I write u by u infinity is equal to a plus b eta plus c eta square plus d eta cube and so on. If I am writing as a polynomial in general, because polynomials are generally one good approximations of solving solutions, then you can see using the equations, these are the three physical boundary conditions what we get. Okay, and there is nothing unsteadiness, so no need of any initial condition. Okay, so three boundary conditions. So maximum how many unknowns you can solve using these three boundary conditions? You can solve maximum 3 unknowns, right? So if you can solve maximum 3 unknowns, I have to restrict this up to here, because 1, 2, 3 constants are done. Okay, and in this, if you put these 3 boundary conditions, these are the constant values that you'll get. Beta will be 2, c will be -1, a will be 0. These are the constants for these 3 boundary conditions in this quadratic profile. That's how you'll get this profile. Okay, so that's why this profile is a bit important, and you see that profile many times in all the fluid mechanics books. Okay, clear? You might have seen this profile many times. Actually, the reason why you see this very frequently is because of this. If you want higher accuracy, you can still define more boundary conditions, like the second derivatives are zeros, all the things. You can extend this up to 4 or 5 sequences. But again, calculation of these basic things, bit, theta, all these things will become very elaborative. That's it. Okay. So anyway, this is the quadratic thing. Okay, I'll leave that. Fine. Somewhere you can see. Now, actually, if you calculate theta for this, if you do the integration 0 to delta u by u infinity 1 minus u by u infinity dy for this, you will actually end up with, after doing, look, it is very simple integration. You need not do much. You keep this term here, 1 minus of this, you multiply them, you will get some terms, some 6-7 terms you will get, just integrate. Okay, single variable integration. It's a one variable integration. You need little patience to do it. That's it. Okay, and little carefulness, because no plus or minus sign should go actually. So if you do this calculation, finally you will end up with 2 by 15 times of delta. Okay, I'm giving you the result, but in your free time, please try this. Okay, then let's see. In this case, why I'm talking about theta very crucially is, finally your ultimate idea is to calculate delta in terms of system parameters. Okay, not in terms of conceptually it's depending on delta, all these things, but practically you should know that looking at let us suppose if there's a flat plate and fluid flowing. Basically, what are the things you can identify? You can say what is density, what is dynamic viscosity. At some location, you can take a scale and measure x. So you should be able to take delta in terms of some system parameters, something which you know. Okay, not conceptually that delta is something of integration of delta, nothing like this. You should, by looking at the system parameters, you should be able to understand how to calculate this delta. So for that, we calculated the momentum one-Commons integral equation. So one-Commons momentum integral equation. So let us see. This is 2 by 15 times of delta. If you keep in one-Commons momentum integral, tau w is also nothing but mu into du by dy, because it's only function of y. So du by dy at y is equal to 0. Okay, if you differentiate this, you will get mu into 2 by delta minus 2y by delta at y is equal to 0. Okay, so if you put y is equal to 0, this guy is 0 clearly. So we have 2 mu by delta into u infinity. U infinity is also there, because if you differentiate, this u is equal to u infinity times of this. So you have a u infinity 2 mu u infinity by delta. Okay, so this is what you get, 2 mu u infinity by delta. Now this is tau w, and if you have this theta 2 by 15 delta, so you can put it in Von-Karman's momentum integral equation. If you substitute, since for flat plate, this is only for flat plate, okay, the actual Von-Karman momentum equation is something different, what I have shown you. For flat plate, tau w by rho is equal to u infinity square d theta by dx. So what is tau w? You have calculated 2 mu u infinity by delta is equal to u infinity square d theta by dx. So 2 by 15 d delta by dx actually. Okay, this is what you have. Now clearly you can understand something. 2 gets cancelled. U infinity can eliminate this. So 15 by 2. No, 2 is not there now. 15 mu by u infinity. Okay, so this is the term 15 mu by u infinity dx is equal to delta times d delta. Now this is a first order differential equation divided by density. Yeah, density should also be there here. Okay, so density should also be there, correct. So density is there. Now if you see this is the first order differential equation which is in variable separable form. Okay, now we have to solve this. Now to solve this we need one boundary condition, yes or no, because it's a one dimensional spatial equation. So now clearly it's a first order differential equation. To solve this we need one boundary condition. What is that boundary condition? Clearly, you know, loosely we can say at x is equal to 0, delta is also 0. So at some x, what is delta? That's what. If you integrate, you can see 15 mu by rho u infinity x is equal to delta square by 2. So delta is equal to 2 15s are 30. Okay, so 30 mu x by rho u infinity. If you make some simple adjustment here with a x and square, we can see delta is equal to square root of 30 into square root of x square is x divided by, if you write this mu here, this is nothing but your localized Reynolds number. So to get this constant, we have to know what is Von-Karman's momentum integral equation, and you have to solve the equation. But with the help of scaling analysis, without this constant, you came to know that using scaling analysis, you found out this delta is going to depend on inverse of square root of Reynolds number. You understood this? That's the power of scaling. Understood? So scaling analysis will actually give you complete things except the constants. So for getting that constants, you do a mathematically rigorous process and you finally found out the constant value. But scaling told you without this constant, this delta is going to depend upon square root of Reynolds number. Clear? That's the important thing. And to calculate delta, you see everything is known to you. You can know what is delta, mu, u infinity, you know, x you can measure easily. So in terms of system parameters, you are able to calculate what is delta. Got it? So at the end of the lecture, can you explain how to balance college studies and GATE preparation in second and third year? I'll tell you in tomorrow's session. Okay, please, because the time is up actually today. Because the concepts are connecting. If I leave in middle, you cannot again make contact. That's why. Okay, so this is 30. So delta is actually 30. So clearly you can understand one thing. Look, in this analysis, you can understand, or here, all these are constants. You came to know delta is proportional to square root of x in laminar. Because everything we have taken only for laminar, no turbulence. So delta is proportional to square root of x. Okay. So does this delta is independent of given velocity profile? No, it's dependent because this 2 by 15 is depending on velocity profile. Understood, Banu? If this profile changes, this 2 by 15 changes. Okay. So basically, in any kind of profile, only the constant changes. This x by root ix will never change. That's what even scaling told us. When you do the scaling analysis here, when you do the scaling analysis, you can see that's what you got even in this. No, it's not dependent. You have it on dependent only, no? Correct. It is dependent actually. Now, anyway, now one important point is, so we found out delta is actually proportional to root x. which means as x increases, delta also increases, which we understood physics from physics point of view. Here in the beginning itself, I have told you, like I made you understand one thing, that as x increases, delta also increases. But then at that physical level of understanding the problem, we don't know what is the mathematical variation. Okay, but after working out through some equations, we found out delta is actually function of square root of x. Right, now let us talk about tau w, because with very hard work we have calculated tau, this delta. So let us see, tau w at any location is 2 mu u infinity by delta. Okay, so this is the case. So 2 mu u infinity by delta. So what is delta here in this case? If you see, 30 square root of 30 into delta is square root of 30 into root mu x by rho u infinity actually. So you can do one thing, you can actually write this as, okay fine, you can understand one thing. In this equation, if you see, all are constants except this x, so tau w is equal to some constant times 1 by root x. You understood this? Okay, so tau w is proportional to 1 by root x, which means as x increases, your tau w will decrease, which also you understood from physics of the flow, that before this non-dimensionalization and all the these things, you can see as x increases, tau w decreases from physics of the problem. Understood? Because I'm extending this class because I want to connect all these things which I have explained you physically with mathematical things which we have calculated much later. Okay, fine. Is this clear to all of you? Now did you all understand the connection of understanding the physics and working out to the maths and the power of scaling, which we have done here in this case? This is anyway equations. So scaling, bit of scaling the terms and understanding dou p by dou y is 0 along the cos time coordinate, then after x. Can you connect all these things? Okay, the only thing is you have to do a bit of integrations. Okay, and I'm not going to teach you integrations because anyone can do that. I hope at least at this level of you can do. Let us suppose if I give you some function, for example, if I give you this velocity profile, you know how to calculate theta. Okay, just put these expressions here and here and do the integration little peacefully. That's it. Okay, fine. Then let us see what we have. I think then that's all we have. I thought of solving some dimensional analysis also today, but fine, time is up. But are you all understanding the things? Because I know boundary layers is one of the die areas where many of the students don't understand much conceptually, but they just by heart this displacement thickness, momentum thickness and all. But actually the actual points you should understand is something beyond that in boundary layers. Okay, all this is about lambda boundary layers. Clear? Is everything clear? So we'll write some summary. What we have done today, we have done basically the boundary layers. That's it. Okay, and we have worked out to, let's quickly revise what we have learned today in today's session. Let's quickly go through that. So this is a recap anyway. So boundary layers we have seen. Normally if you take a boundary, what happens to different velocities at different points, and we have defined two coordinates x and y. So then after we understood that these are the main equations, and boundary layer equations are some approximations of this. So streamlines of the flow will diverge in the downstream. I explained you why using flow, and this physically I have shown you how this x increases with delta and wall shear stress will decrease with increase in x. Then after we worked out to scaling analysis. So in scaling I have shown you how to scale different terms. I have explained you how this scaling of v happens in general, and also I have talked about this scaling delta by L whole square. We have seen certain terms. Finally we understood that this is 0 not only for flat plate, for any boundary layer. Okay, so then we have again seen that delta is proportional to L by root IL, all these things. Now in case of inviscid region, this term can be replaced with this, and clearly in boundary layer equations we have seen this can be replaced. Okay, so for flat plate this term is 0, so dp by dx is 0. Pressure is constant at all points in the flow. Okay, then after we have seen some basic stuff, displacement thickness, momentum, energy, all these things. Then after the momentum integral equation, applying some control volume balance could easily, just one equation, okay, momentum equation and mass balance could give this, and this is the equation for flat plate. For flat plate, then we have solved one example by taking one velocity profile, so that I have shown you using one command's momentum integral equation how can you calculate wall shear stress and this delta in terms of physical system parameters. That's it, okay? Because physically, if you see a flow, you know density, dynamic viscosity, you know all these properties. That's it, okay? So you should be able to talk something about delta, tau w, all these things in terms of known system parameters, okay? Because you never know what is this. If I give you this equation, by looking at this, you don't know this and you don't know this. Then how can you define? So you should know some way to calculate. This is the simple integration what we do. Clear? So that's what you have. And anyone, if you feel like, anyway, these topics I think I didn't find time, so I will not cover today maybe, but later. So if some of you want to join the group, you can join here. This is the group, okay? Normally you can post any mathematical questions. Normally the subjects that ideal is all the thermal related subjects, fluid, heat, thermo and applied, and maths, okay? So you can talk about this, fine? So thank you all. Then we'll meet tomorrow at 7:30 AM and we'll discuss certain things. We'll see dimensional analysis and also turbulence we'll see a bit. Compressible flows I will teach, okay? Because potential flows, these lectures are anyway uploaded in the English channel, so better you go through them. Only 4 lectures are there, okay? So you can go for roughly 8 hours of videos. They are detailed course, okay? Those 4 videos are from detailed course of fluid mechanics, so you can find each and every self-explanating, okay? So please, for potential flows, refer that, because it's taught in complex numbers. It will be much advantage for you. Will you teach maths in this course? No, I think Rahul sir will take maths in the fast track, okay? Because I have some other commitments again in the other batches, okay? Fine. So take care. We'll meet on tomorrow at 7:30. Bye. Signing off. Any doubts, by the way? Okay, no doubts. Then thank you all. We'll meet tomorrow. Take care. Bye.